Okay, beginning our first chapter on forces. We're going to be talking a little bit about force, what a force is, mass, and introducing Newton's first law. So first, let's start with force. Fundamentally, most simply, a force is that which causes an acceleration. So in the absence of forces, you won't get accelerations. However, you can have no acceleration but have forces acting. We'll get to that more with the second law than with the first. Alright, well, if there's something that causes an acceleration, is there something that can resist being accelerated? And inertia, or mass, resists being accelerated. The more mass you have, the harder you will be to accelerate. That's one way of thinking about things anyway. We do measure mass in kilograms. Pound is really more a measure of a force, but it's about 2.2 pounds to be 1 kilogram, so about a pound is about a half a kilogram, very roughly anyway. Most people in the class are probably between 50 and 100 kilograms. That's 110 to 120, so, sorry, 220 pounds. Could have people that are each a little lighter or a little heavier than that, or a little bit more or less massive than that. All right, how does this all relate together? Well, kind of we're looking at Newton's first law. So the first law of motion in its most simple form just reads something like an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an unbalanced force. If the forces are balanced, if you have equal but opposite forces acting on an object, then its velocity may remain constant, either at zero or non-zero. If the force becomes unbalanced, you expect to experience an acceleration. This will no longer be true that you are at rest or at motion without changing. So, in the presence of an unbalanced force, or a net force, you will see accelerations, and in the absence of a net force, you'll just see that an object at rest stays at rest, and an object in motion stays in motion. Now, this is kind of a fun topic to talk about because the first part of the statement makes a lot of sense. An object at rest will remain at rest. Great, I take the pen, I set it on the table. It sits on the table and it stays there. I take the calculator, I put it in my hand. It sits there, it's not moving on its own. Object at rest remains at rest. Awesome. It's a little bit trickier thinking about an object in motion remains in motion, because you take a ball and you throw it, and it bounces around, hits the ground, and it eventually completely stops. So we don't really see an object in motion remains in motion forever on the surface of the Earth. And if you're wondering why that is, it's the unbalanced force aspect of this. On the Earth, there's always resistive forces. At a minimum, there's air resistance. Sometimes there's rolling friction. Whenever there's interactions between objects, there does tend to be some interactions that take away some of the energy. End result is the objects experience little forces here and there that eventually bring them to rest. If you watch videos of astronauts playing around, there used to be lots of videos you could find of astronauts playing with their food. They'll send a banana spinning slowly across the cabin of the spacecraft, and someone will catch it. It's a little bit like you've seen The Simpsons, the episode where they send Homer to space, and there's the donut coming across and chomp. It's really very much like that. An object in motion will stay in motion for a very long time because there's only air resistance force, and air resistance force for slow-moving objects is very low. So that is the trick. If you take away the air completely, for instance, an object in orbit around the Earth, particularly geosynchronous or geostationary orbit, that's far enough away you don't really experience any air resistance because there's not any appreciable air at all out there. So you can put stuff out there and reasonably expect it to stay in the same orbit for thousands of years, more or less. The moon will occasionally come by and bump it enough to change its motion slightly, but generally it will stay moving for thousands of years. And take the Voyager spacecraft. It is now over a light day away from the Earth, I believe. And it's going. We don't know exactly where because we don't know exactly what objects it's going to interact with gravitationally, but it's been given its speed and it's going to keep trucking along as gravitation doesn't tug it somewhere for pretty much as long as matter exists in the universe. So provided you can get into an environment where we don't have to worry about resistive forces like air resistance, that object in motion will remain in motion. Anyway, there are kind of fun examples of inertia, and maybe I'll see if I can find one. There's a simple one you can do at home. Get a cup, get an index card, sit the index card on top of the cup, and put a quarter on top of the index card. Then flick the index card out of the way. It's the same trick you see when somebody pulls the tablecloth out from under the dishes. Essentially, the dishes or the coin have mass. They have inertia. They don't really want to go anywhere. You're going to have to exert a significant force on them to really accelerate them. So if you take the card and you suddenly forcibly accelerate the card, and there's only this tiny friction force to act on the tableware or the coin, and you should be able to flick the card out of the way and have the coin drop nicely into the cup. You can actually do this with a bottle if you're careful enough. You have to be careful not to flick the card upward, for instance. But yeah, it's a demonstration that an object at rest remains at rest, and an object in motion remains in motion, particularly in this case, the object at rest remaining at rest. There's another fun demonstration. I'll have a quick poke and see if I can find it on YouTube. I do not have the capability to really record this one here because I'm likely to break stuff. But if you take a mass, heavy mass, and you hang it with a piece of string, then you put another piece of string underneath. Imagine you grab the piece of string on the bottom and pull slowly, increasing the force bit by bit. The upper string will be the one to break because it experiences the load of the mass gravitationally and your pulling force. But here's where it gets interesting. If you set the same thing up, string at the top, heavy mass, your string at the bottom, and you yank it very quickly downward, you'll actually break the bottom string. And the reason for this is the mass does not want to move anywhere, and you've got to provide significant force to accelerate it. And you end up changing the motion of the string fast enough that it doesn't efficiently get transmitted through. It's essentially blocked from transmitting through by having to first accelerate the mass. So you end up breaking the bottom string. Very cool demonstration of an object at rest remaining at rest and some of the interesting consequences it can cause. I don't recommend you try this, but another demonstration of more or less the same thing is putting a heavy weight on your head, like a great big block of wood, and then pounding a nail into it. Of course, if you tried hitting your head with the hammer, you'd really damage yourself. But the fact that you have to first accelerate the heavy block of wood before you can damage the head, it's not as bad. I still don't recommend it. Don't try this at home. Alright, so that was lots and lots of talking, but I got the principles across. I'm going to stop here, and we'll get into more about Newton's laws and forces next time.